Hello everyone, welcome to our presentation about the use of state tree to implement the AI of Dinosaurs for the survival game Gunner. My name is Corentin Lemasson. I'm a lead software engineer at Black Shamrock for 4 years now. Before working on Gunner, I was working on an action RPG for 3 years, and I specialize in gameplay and AI programming.
And howdy folks, my name is Florian Peters. I'm a software engineer at Black Shamrock, where I've been honing my skills on gameplay programming and AI development.
Black Shamrock is a studio that provides co-development services for any type of game on PC and consoles. It's part of Virtuos, a group of studios all over the world that have different areas of expertise to better support our client. What is Gunner? It is a single-player survival game developed in Unreal Engine 5. It is still in development by local players, a studio in the Canary Islands, with Tate Multimedia as a publisher. When we started to work on Gunner, the AI was implemented using behavior trees, but most of the behaviors were not working as expected and were quite difficult to debug. That's why a local player and Tate Multimedia asked us to help them to get the AI development back on track for a successful release.
So first, let's talk a little bit about the Gunner game and its project design requirements. First, you should know that Gunner features a large range of diverse species of fauna that have it's a large range of different scales for the dinosaurs. Which they go from the chicken-sized Richardo-Estesia to the towering Alamosaurus, which is around 20 meters high. These wildly different scales imply that we needed different navigation grids for the agents, which was done using the Mercuna navigation plugin. Different scales imply different animation needs, and thus we needed a flexible animation system that would be able to play similar animations for similar actions, but with drastically different visuals and potential lengths. It is also important for the game's intention that the player feels like a part of a larger ecosystem. And to that effect, there are plenty of wildlife simulation systems that have been implemented. The dinosaurs get thirsty and hungry. There is a dynamic between herbivores and carnivores, as carnivores go into predator mode and start tracking their prey, and a bunch of additional systems, such as a fear of fire, be it a torch held by the player or a source of open flame like a campfire, dinosaurs becoming more aggressive in groups, and a nest defense system. And finally, the game features some combat and stealth, so combat between dinosaurs, and due to their variously different scales, they need to be aware of how much space they occupy and be able to position and navigate in between one another. Combat with the player combat for the player is very risky, which means that stealth needed to be an important component for the game. And so the dinosaurs never perceive the player's location directly. It's always via proxies using AI senses, such as sight, hearing, or smell. So in essence, the abstract problem that we're trying to solve here is the following. We have our game world, and within that game world exists our agent. The game world feeds information to the agent via a data stream that we will call the context here. And inside the agent's brain happens a decision-making process that figures out which is the correct or most favorable action to take given that current context. And that action is then given into the game world. The process of determining that action has been studied extensively over the years and solved using various techniques with advantages and disadvantages, such as finite state machines, behavior trees, GOB, HTNs, what have you. In our case, as mentioned earlier, it was done using behavior trees, and we could clearly see that this was going to be a hindrance for the project going forward, and we decided to switch over entirely to the newly developed state tree mechanic. And we'll showcase those advantages in the following sections.
So state tree in Unreal Engine is a framework that allows you to implement complex AI behaviors, just like behavior trees was able to before. It provides the advantages of state machines with transition and states, and of behavior trees with the hierarchical aspect. Agents each have their own state for the execution of a tree, and have their own data. But they can also share data if they are running the same state tree asset. State tree can be a bit challenging to start with because the documentation lacks details and there's not that many state tree task example to follow. Just to present a bit how it works, here's our main state tree asset for the game in the state tree editor. And on the left, you can see the parameter of a state tree. In the middle, the hierarchy of state. And on the right, the tasks for the state currently selected. Now let's go over how state tree works and how it differs from behavior tree. State tree acts like a state machine, but is built as a hierarchy of state that can be active at the same time. In this example, you can see that the root state is active, as well as the aggressive state down to the normal attack state. When tasks run inside the state tree, they are going to run sequentially. So starting with all the tasks on the root state, same for the aggressive state, etc., till it reaches the normal attack state. Tasks are quite easy to define, and the advantage is that there's no distinction between tasks that do actions, like moving the character or playing an animation, and tasks that just generate data. So that's a good advantage over behavior tree that has like decorators and services. Here you can like reuse the code and just do everything with tasks. It's also much faster to implement because you don't have to interact with the blackboards. Data bindings is another big advantage of state tree. Because any task can produce data that any other task can consume. So that provides a sort of like clear scope for the data. Each time that you want to consume some data, you'll see the list of data available that you can consume at any point in the state tree based on the previous task that can potentially run. And that's a big advantage over blackboards again, because blackboards, you never know if your data is valid, you never know if it has been produced at that point. In this example, you can see that we have two tasks that are on the root state. The first task is thirsty, will produce a Boolean value that the next task should drink and consume to produce its own value, which creates a nice pipeline of data. Transitions are also easy to define, and they allow to have like a great control over the execution of the state tree. That's compared to behavior tree, where the constellations of the behavior tree branches are quite confusing. You never know like if this is going to be the lower priority cell that is going to console and where exactly. In a state tree, it's much easier to follow that. Here's an example where we define a transition from the active state to the forget state, and how it would be executed at runtime, and whether or not the conditions to do this transition are going to be successful.
So while state tree provides an efficient and quick way of defining new behaviors and actions, it doesn't provide that higher level abstract thinking of what action should I take next. And this is the solution we came up with, which uses, it's in a couple of steps. We'll just go over them right now. First, we have the AI perception system, which is a native system available in Unreal Engine, which handles all the senses for the agent, so sight, hearing, what have you. And it generates a list of perceived stimuli for that agent during that take. That list is fed into a custom system, the perception stimuli sorter, which, according to predefined rules, will sort the stimuli from most important at the top of the list to least important at the bottom. And it also returns the highest priority stimulus for the source actor. That list of stimuli is finally sent into our state response selector. So this is the system that actually figures out, according to the stimuli, which action to take at that moment, or which state to go into. And in the actual state tree, this is where we have that process. So with the root node selected, we can see at the bottom right here in the tasks, there's the sort perception stimuli task and the select main state task. And let's dive a little bit deeper into how this stimuli sorting is performed. Let's do it with a toy example here. Let's say I have a sight stimulus of a neutral actor, a touch stimulus by an ally actor, a smelling stimulus by an ally, and finally a hearing stimulus by a hostile target. The sorting is done in broadly two categories of steps. The first of which are the filter steps, which, as the name implies, simply discard the stimuli that are not relevant for that tick. In this case, it will simply discard the ally stimuli since we probably don't want to react to our allies right now since there's neutral and hostiles. The second broad category of steps are the score and sort, which will generate, according to different scoring criteria, a score for each stimulus. In our implementation, those scores are appended into a bigger meta score, which is then used to generate the final stimuli list. And in this example, we see that the hostile target has been selected as the highest priority stimulus for that tick. In practice, the actual task, here's what we have. In blue are the filter steps, which in here only consist of one step. And in orange, the score and sort steps. The filtering is only done for the expiration date for the stimulus, so anything that's longer than, say, 5 seconds is simply discarded. And in the score and sort, you can see there's various scoring criteria that we use. We have a team attitude one, a threat level, age, and senses. Senses are particularly important since you want to react to, say, for example, damage or touch. It's more likely you want to react to those stimuli rather than, say, a smell stimulus. As a side note, the threat level is a particular mechanic implemented in Goner. It is a single value that defines how threatening a dinosaur or an agent is relative to others. So let's say you're a medium-sized dinosaur of threat level 5. You probably don't want to react to the small Richard that's probably threat level 2, and you probably want to prioritize reacting to the T-Rex threat level 8 or 9. And finally, the last step in index 6 is the sort by scores, which simply creates that final ordered list of stimuli. And at the very bottom here, you can see the bindable output in the task that is then fed into our state response selector.
Now that we have the perception stimuli of the agent sorted, we need to decide what the agent is actually going to do. To do that, we use a pipeline of actions similar to how we sort perception stimuli. We're gonna as the first action, we're gonna append all the states that are available. And the next actions are progressively going to filter which states are actually available based on the current context. In this case, we can see that the sleep state is filtered because it's not nighttime, while the roam and the nest states are always available because there's no condition attached to them, which allows a nice fallback for the agent to always be able to do something. The search state is also available because in the previous example, we heard a hostile actor, so we'll need to search for that noise. When filtering these states, the context that is provided includes all the target actors and associate a state to each one of them. What it allows us to do is to have a progressive reaction to react to a target. When we hear a sound, we're going to go to search for it. And then as we search, if we see it, we're going to be able to turn aggressive and maybe move towards it and attack it. Some states don't require any target actors, like the hit state, that only depends on one of the attributes of the agents, like whether or not it is angry. Once we have all the states that are available, we need to generate a transition to one of them. Each state has got a priority and a weight, and what we're going to use is the priority to sort them. And if two states have got the same priorities, we're going to decide which one comes first based on by selecting one randomly based on their weight. After that, we just loop through each one of them, and we generate a transition request. Here it says critical, high, and normal because this is the transition requests that are available in state 3 to generate transition requests dynamically. We only generate a transition request if the priority of the state is higher than the one currently selected. What it does is that it avoids these oscillations between states of similar priority and allow the agent to finish an actual task. We also are going to generate multiple transition requests, because that way we can have a fallback if one of the transition doesn't work. Because there can be like enter condition on each state that are a bit different from like the one we use to filter. So that way we make sure we always have something, a valid transition to do. The last step is to output the highest priority stimulus so that we have it available for the state that we select to to use in their behavior and react to the most important targets from the agent's point of view, so based on the threat level and whether or not it's hostile towards this species. This is how the state response selections looks in practice as a state tree task. So you can see that it's an array of instance objects that we are going to run sequentially and that are going to process this array of states. It kind of uses like something similar to utility AI because it's going to consider all the actions that the agent can do before selecting one. We could improve the system. We didn't have time to do it. We could improve it by having a scoring function for each weight so that there's a bit more randomness, I would say. Now that we have decided what to do, it would be good to implement the actual behavior to do that. The problem is that when you start to use state tree, you won't have that many tasks that are available to use on actors. That's because Epic focused mostly on mass entity at first, so they implemented everything related to that, but kind of skipped the actor part. So what we suggest is that you implement a toolbox to have all the tasks that you need to create any kind of behaviors. You can, for example, start by a task to move the character or to rotate it. Other tasks that are quite useful are tasks related to animations, so playing an animation montage identified by a tag, or setting an animation state. Animation states are especially useful because they allow you to decouple your AI logic from your animation logic. So what you can do is you can set an animation state for the character to be idle, for example, and wait for the animation blueprint to decide when it's not idle anymore, and the state tree can resume its AI logic.
At some point during development, you'll probably also want to expose your underlying engine systems to the AI. And to that effect, we recommend adding another set of tasks to your toolbox, which are interfacing tasks. What they do is essentially they wrap around the systems in a nice way so you can use them appropriately in state tree. In our case, we used it for the gameplay ability system to trigger abilities and get attributes, for the environment query system for positioning and navigation, and the navigation system itself to actually move the character around and for pathfinding. We also had a couple of tasks to handle interaction with the smart objects. And the final set of tasks that we recommend adding to your toolbox are meta tasks. Meta tasks are a bit funky tasks. They allow you to control the flow of the state tree directly in a task. Here are a couple of examples. In our case, we implemented a run state tree task, which, as the name implies, allows you to run a different state tree than the one you're currently in, which sounds a bit crazy when you think about it, but you will realize that this is actually extremely useful for development, since it will allow you to decouple parts of your AI logic from the main state tree, which then you can use to develop separately and not have like any conflicts between one another. Another task that can be useful is a send state tree event, which will allow you to just send a gameplay event via a gameplay tag from the state tree, and the state tree can react to that gameplay event. This can be useful, for example, if you want like a break condition, if you're running a state tree within a state tree. So from the child state tree, you would send the state tree event to the higher level state tree in order to break out of that loop. And the final task that we recommend adding is a block/replace transition request. So that one will essentially just block any sort of transition in your state tree, even if there's a transition generated during that tick. That can be useful if your AI is currently, let's say, sitting down in a nesting stage, and suddenly there is a hostile target coming in the nest. you probably don't want to kick in the aggressive behavior immediately. You want to first get out of the nest state smoothly and to perform the animations correctly. And during that part of the animation, you want to have that task to block any sort of transition requests and only trigger them once the state has properly finished. And we believe with that set of toolbox tasks, you will be able to create complex and rich AI behaviors using state tree.
Thank you so much for your attention.